In the frozen emptiness of deep space, 13 billion light-years from Earth, something impossible is staring back at us. The James Webb Space Telescope has opened its infrared eyes, and the universe has begun to reveal a version of itself that breaks the rules we spent a century believing in. What Webb has seen is not simply unexpected. It is catastrophic. Ancient galaxies that grew far too fast, black holes older than the first stars, rogue planets whispering strange radio signals, and a cosmic expansion rate that behaves like a malfunctioning machine. Tonight, we dive into a darkness older than time, into a cosmos that refuses to obey the laws we built to explain it. And if you are ready to follow the faint light of ancient stars into the unknown, then we begin. For decades, cosmology felt stable, predictable, almost comfortable. We knew how fast the universe was expanding. We calculated its age. We believed we understood how galaxies formed, how stars ignited, how gravity sculpted the cosmic web. Hubble gave us one number, theory gave us another. The mismatch was small, easy to ignore, easy to blame on calibration or dust or uncertainty. But then James Webb arrived. Its precision unmatched, its sensitivity extraordinary. Webb looked deeper, farther, and cleaner than any instrument before it. And what it found was not a small inconsistency. It was a fracture, a crack running straight through the foundation of cosmology. Webb confirmed that the universe is expanding at two different speeds, depending on where you measure it. Imagine inflating a balloon. The top half stretches rapidly, while the bottom half barely changes. That should be impossible. Physics demands uniform expansion. Yet the universe is not playing by that rule. Webb measured distant Cepheid variable stars, the gold standard of cosmic distance markers, and got one expansion rate. Then it looked at the cosmic microwave background, the ancient afterglow of the Big Bang, and got another expansion rate entirely. Not a small difference. A chasm. A contradiction so enormous that Adam Rees, the Nobel Prize-winning scientist who studied it, said, "If measurement errors are ruled out, what remains is the real and exciting possibility that we have fundamentally misunderstood the universe." But exciting is a gentle word for something this world-shattering. If the expansion rate is inconsistent, then our entire model of the cosmos may be wrong. Dark energy might behave differently in different regions of space. The age of the universe may be miscalculated. Space-time itself may contain unseen forces or fractures. This crisis is called the Hubble tension. But tension does not convey the horror of watching the universe fail to follow its own rules. It feels more like reality is glitching. Like the cosmic program we believed in is running two incompatible versions of itself at once. Yet this was only the first blow. Because as Webb gazed deeper into the ancient darkness, it found galaxies that should never have existed. When astronomers pointed Webb's infrared sensors at a tiny, empty-looking patch of sky near the Big Dipper, they expected faint baby galaxies. Small, fragile, barely beginning to form. But instead, they saw monstrosities. 6 massive, mature galaxies, each containing tens of billions of stars, fully grown when the universe was only 3% of its current age. To understand the absurdity of this, imagine planting an acorn and 3 months later finding a towering oak tree. Star formation takes time. Gravity must gather gas and dust over millions of years. But these galaxies behaved as if they had a cheat code, forming hundreds of stars per year, racing through the cosmic childhood in a frenzy no model can explain. Erica Nelson, one of the researchers studying these objects, described them as universe breakers. Because if these galaxies are real, as Webb's spectrograph confirms they are, then our timeline for cosmic evolution is catastrophically wrong. The early universe was not slow, gentle, or simple. It was a storm, fast, organized, chaotic, and creative in ways we never imagined. And this storm produced something even stranger. Deep in the ancient cosmos, Webb found a supermassive black hole, 50 million times the mass of the Sun, drifting alone. No galaxy, no stars, no host. A homeless gravitational monster. Normally, supermassive black holes sit at the centers of galaxies, growing alongside billions of stars. But this one, named Q-Son, floats naked through space, violating every rule we thought was unbreakable. And the worst part? It existed only 600 million years after the Big Bang. That is far too early for a black hole of this size to form through normal processes. Scientists proposed 3 explanations, each more disturbing than the last. The first, Q-Son could have formed through direct collapse, skipping the entire star phase and forming straight from a massive cloud of primordial gas. The second, it might have consumed matter faster than physics should allow, breaking the Eddington limit. And the third, the most terrifying, it could be a primordial black hole, a relic forged in the first seconds after the Big Bang, when space-time itself was unstable and dense enough to collapse into black holes without stars. If that is true, then primordial black holes could be everywhere. Millions of ancient monsters wandering our galaxy, older than any star, older than light itself. And Q-Son is only one of many. Webb has found dozens of these red, compact objects scattered across the early universe, each one glowing with the light of matter being shredded and devoured. They hint at a cosmos far more violent than we ever imagined. But Webb's revelations didn't stop there. The telescope found black holes that existed before the first stars. That alone rewrites the story of cosmic dawn. Our old sequence, stars first, black holes later, is broken. Webb's data suggests that black holes may have been among the first luminous objects in the universe. Andrea Ferrara and his team propose a radical idea. Primordial black holes heated the early cosmic gas, emitting brilliant halos of light that masqueraded as young galaxies. This means the first radiant objects after the Big Bang were not stars, but black holes, creatures of pure gravity lighting up the infant universe. As Webb continued to peer into the darkness, it discovered something even more bizarre: a cosmic wreck. 2 massive disk galaxies colliding head-on, forming a shape that looks like the infinity symbol. Beautiful, yes. But the beauty hides something unprecedented. At the exact center of this galactic crash sits a supermassive black hole. Suspended, balanced, not pulled toward either galaxy as physics demands, but floating in the middle like a cosmic judge observing the collision. Astronomers Peter van Dokkum and Gabriel Brahma believe we may be witnessing the birth of a direct collapse black hole. The gas streaming between the colliding galaxies became so dense and massive that it collapsed into a black hole instantly. If this mechanism is real, it explains why the early universe is full of supermassive black holes that grew too quickly. The cosmos in its youth was not only chaotic, it was efficient. It created monsters at a rate we never predicted. But the next revelation would take us far from galaxies and black holes into the realm of planets. And what Webb saw there challenges the very definition of what a planet can be. In the Orion Nebula, Webb detected more than 500 free-floating planets. Rogue worlds. Homeless giants the size of Jupiter, wandering through interstellar space with no star to call home. But the strangest part? Many of them travel in pairs. These are Jupiter mass binary objects, jumbos, and they are not silent. They are emitting radio signals unlike anything we have ever detected from planets. High-frequency gigahertz bursts, far above the frequencies emitted by natural planetary magnetic fields. The signals resemble the outputs of technology or extreme astrophysical objects, like pulsars. But these signals are coming from planets, orphans drifting in the cold. Scientists think the answer lies in their binary nature. Two massive planets orbiting each other create swirling magnetic fields and colossal electric currents, cosmic generators unlike anything in our solar system. But the fact that these signals exist at all suggests processes we have never observed. And the fact that there are hundreds of these paired planets in a single nebula implies that the galaxy might contain billions. Entire solar systems may have collapsed or ejected their worlds into darkness. These planets wander forever, circling their companions, their only warmth coming from internal radioactive decay and tidal forces. But Webb did not stop at rogue planets. It discovered planet-forming disks unlike anything in our models. Around the young star XUE-10, Webb found a disk almost entirely devoid of water, yet full of carbon dioxide. This contradicts the most basic rules of planetary chemistry. Earth-like planets should form in regions rich in water vapor and silicate minerals. But XUE-10's disk is dry, hot, and carbon-rich, creating planets that would be totally alien. Worlds with no oceans, no water cycles. Planets built from carbon dioxide ice and exotic minerals. If UV radiation stripped water from this disk, as one theory suggests, then potentially habitable worlds across the galaxy may never receive the ingredients for life. The diversity of planetary systems is far greater than we believed. Entire classes of worlds may exist that defy our imagination. And still, Webb pushed deeper. It found a hell world, 55 Cancri, where a year lasts 18 hours and the day side is hot enough to melt copper. A world that should have lost its atmosphere billions of years ago. And yet, it has one. An atmosphere rich in carbon monoxide and carbon dioxide, swirling around a planet that glows like molten metal. Supersonic winds carry vaporized rock from the blazing day side to the frozen night side, where it condenses and falls as mineral rain. The atmosphere should not exist. Solar radiation should have stripped it away. But new gases constantly boil up from the planet's interior. This world is cooking itself alive, its crust vaporizing and rising as atmospheric gas before raining down again like molten stone. A planet-sized distillation machine operating in conditions no human laboratory could reproduce. And finally, Webb looked closer to home and found an ancient traveler, Comet 3I Atlas. At first glance, an ordinary 7-mile-wide chunk of ice and rock. But its trajectory reveals its origin, the thick disk of the Milky Way, a region of ancient stars. Webb's instruments determined its age, 7 billion years. It is older than the Sun, older than Earth, older than every planet in our solar system. This comet has been wandering through interstellar space since before our world existed. Its chemistry is frozen history, a sample of a long-dead star system that vanished billions of years ago. It races through our solar system at 130,000 miles per hour, following not the gravity of the Sun, but the gravity of the entire galaxy. An interstellar messenger passing briefly through our neighborhood before disappearing back into the darkness. When you look at all these discoveries together, the broken expansion of the universe, the impossible early galaxies, the primordial black holes, the violent collisions, the rogue planets, the alien chemistries, the hellish atmospheres, and the ancient interstellar visitors. One thing becomes clear. The universe we thought we understood is gone. In its place stands a cosmos far more complex, violent, creative, and strange than we ever imagined. And James Webb has shown us only the beginning. What makes this ancient visitor truly unsettling is not just what it is, but what it represents. Comet 3I Atlas is not merely a chunk of ice and rock passing briefly through our sky. It is a messenger from a time when the universe was radically different from today. 7 billion years ago, the Milky Way was more chaotic, more violent, and far less chemically evolved. Star formation rates were higher, collisions were more frequent, and heavy elements, the metals that build planets, oceans, and life, were scarce. The physical rules were the same, but the initial conditions were not. In that young galaxy, clouds of gas collapsed under gravity to form a star that lived and died long before our sun even existed. Around that ancient star, in a disk of primitive material, this comet took shape. It froze into existence as a small, silent witness to an era when the building blocks of worlds were very different from the ones we know. Then its parent star died, perhaps in a quiet fade into a white dwarf, perhaps in a violent supernova that shredded its planetary system and hurled its fragments into interstellar space. Whatever happened, 3I Atlas survived. It escaped. For billions of years, it drifted through the dark between stars, a frozen time capsule carrying chemical signatures from a long-vanished world. For 3 billion years, it traveled alone through the cosmic deep, far from any sun, its ices preserved at near absolute zero. And only now, by a coincidence of staggering scale, it passes through our neighborhood, briefly illuminated by the light of a star that didn't exist when it was born. The fact that we can see it at all is disturbing questions. How many other ancient visitors like this are passing through our solar system unnoticed? 3I Atlas is only the third confirmed interstellar object ever discovered, but statistical models suggest that dozens, maybe hundreds of such cosmic time travelers are crossing our neighborhood at any given moment. Most are too small, too faint, too fast to detect. Each one is a fragment of a destroyed system, a survivor of cosmic catastrophes we can barely imagine. They are archaeological artifacts from stellar families that lived and died when the universe itself was young, carrying information about galactic conditions that no star, no planet, no local comet can provide. And 3I Atlas is not just a window into the past. It is a mirror held up to our future. In a few billion years, when our sun begins to swell into a red giant, when its growing heat boils away oceans and strips atmospheres, our own solar system will unravel. Outer planets may be displaced, moons may be ejected, asteroids and comets might be flung into deep space. Objects that once belonged to our world will become interstellar wanderers, drifting between the stars of some distant future galaxy. Perhaps one day, long after Earth is gone and the sun has faded into a white dwarf ember, a tiny icy fragment from our system will pass close to an alien star. Curious beings might aim their telescopes at it and whisper the same questions we ask now. Where did it come from? What did it witness? What kind of world once circled the star that gave it birth? This ancient comet's visit is not just a curiosity. It is a reminder of the timescales we are playing with, of cycles of creation and destruction that stretch far beyond human history. But as strange as this single interstellar traveler is, Webb has uncovered something even more mysterious. An entire population of objects that simply don't fit into any known category. Scattered across the early universe, about 300 tiny crimson pinpricks glow in Webb's deep images. Enigmatic sources astronomers have begun calling little red dots. They are small, extremely distant, and far brighter than they have any right to be. In astronomy, Red light usually tells one of two stories. Either an object is very cool, or it is very far away, and its light has been stretched or red-shifted by the expansion of the universe. The little red dots are definitely distant. They existed when the universe was less than 1 billion years old. But they are not dim, cold embers. They are blazing. They pour out enormous amounts of energy, combining distance, compactness, and luminosity in a way that doesn't match any class of object in the modern universe. Using infrared imaging and sophisticated spectral energy distribution analysis, astronomers identified around 300 of these anomalies in Webb's data. Each one seems to be roughly the size of a small early galaxy, and yet they are far more luminous than models say such galaxies should be at that age. If they are galaxies, then they are unlike any that exist today. Hyper-efficient factories of light operating under conditions we do not yet understand. That alone would be puzzling, but the deeper astronomers looked, the stranger they became. When scientists tried to figure out what exactly was producing all this light, the answers refused to line up. Some of the little red dots appear point-like, tiny, sharp sources that look more like active black holes than sprawling fields of stars. That suggests that at least some of them might be powered by supermassive black holes devouring matter at extreme rates, their feeding disks radiating across the spectrum. But others show hints of extended structure, as if they are truly compact galaxies undergoing extraordinarily rapid bursts of star formation. It is as though the early universe invented a hybrid object, part black hole, part galaxy, part something else entirely. The most unsettling possibility is that these objects represent a completely unknown phase of cosmic evolution, a type of structure that could only form under the extreme conditions of the universe's first billion years. Back then, matter was denser. Dark matter interactions were more frequent. The cosmic web of filaments and nodes was still knitting itself together. Perhaps those conditions allowed for the birth of objects that simply cannot form anymore. Some of the little red dots are sources of high-energy radiation. They emit X-rays, ultraviolet light, and infrared in patterns that hint at violent, chaotic processes. Turbulent accretion flows, jets, shocks in dense gas. Whatever is powering them is operating under pressures and densities that push the boundaries of known physics. Even their distribution is puzzling. They do not huddle together only in places where our models expect early galaxies to cluster. Instead, they appear sprinkled more randomly across the sky, as if they trace some fundamental property of the early universe itself rather than rare, isolated phenomena. The lead researchers have warned that even if only a fraction of these objects are confirmed to exist at such early times, cosmology will have to change. There are simply too many of them, and they are too bright to be explained away as statistical oddities or misclassifications. The little red dots are a sign that our story of the early universe is missing chapters. But perhaps the most mind-bending revelation from Webb doesn't come from a single object or mysterious population, but from the way entire galaxies move on the grandest scales we can see. When astronomers analyze the spins of hundreds of galaxies in Webb's deep, extragalactic surveys, they found something that should not be there: a pattern. Galaxies separated by millions of light years appear to be rotating in coordinated directions, as if they are all participating in a vast, slow-motion cosmic dance. Imagine discovering that every windmill across an entire continent was spinning the same way, even though there is no common wind, no single storm, no obvious cause. The galaxies Webb observed are so far apart that light from one would take millions of years to reach another. They cannot be influencing each other gravitationally on such short timescales. Yet their spins seem aligned, hinting at some hidden order imprinted at the dawn of time. One possible explanation is as audacious as it sounds. The universe itself may have been born rotating. If the Big Bang had angular momentum, if our cosmos started with a built-in spin, then that primordial rotation could have left an imprint on the large-scale structures that formed afterward. Galaxies, clusters, and filaments might, on average, tend to rotate along that original axis, like sparks from a spinning firework fanning out in similar directions. This idea overlaps with a radical framework known as black hole cosmology, which suggests that our entire observable universe might be the interior of a gigantic black hole within some larger parent universe. In that picture, the rotation we see imprinted on galaxies could be a leftover hint of the spin of that parent black hole, stretched and transformed into the structure of space and time itself. The second explanation is in some ways even more unsettling. If the universe was not born rotating, then some unknown influence must be shaping these galactic spins, something beyond our existing theories. Perhaps a new field, a new kind of cosmic anisotropy, or previously unrecognized behavior of dark matter and dark energy on ultra-large scales. A rotating or anisotropic universe would not just be a curiosity. It would alter the very nature of physical law. Space and time might have preferred directions. Some processes might behave differently depending on which way they point. Even dark energy, the mysterious pressure driving cosmic expansion, might not act the same in all directions, causing space to stretch faster one way than another. This could help explain some of the strange discrepancies Webb has seen in different measurements of the expansion rate. And if our universe is spinning inside a larger structure, then our cosmic horizon, the limit of what we can see, is not the limit of reality. Our universe would be just one region within a much larger landscape, perhaps one of many universes, each with its own spin, its own laws, its own story. As disorienting as these possibilities are, Webb is not done dismantling our assumptions. Its deep surveys have captured events unfolding in real time that we once thought were too rare or too brief to watch. The birth of black holes through mechanisms that defy stellar evolution. In a system nicknamed the Infinity Galaxy, two disk galaxies are colliding head-on, forming a shape that resembles a glowing figure eight. But the beauty of that symbol hides a violent and unprecedented act of creation. Suspended between the two galactic cores, in a bridge of glowing hydrogen gas, sits a supermassive black hole that appears to have formed not from dying stars, but from the direct collapse of gas itself. Instead of waiting for massive stars to live, die, and leave behind black hole remnants, this region of space seems to have skipped that step entirely. As the two galaxies crashed into each other, they created enormous streams of gas flowing between them. Under exactly the right conditions, dense enough, massive enough, cool enough, those gas streams became gravitationally unstable. They collapsed inward not to form stars, but to form a black hole in one catastrophic plunge. No intermediate stars, no supernova explosions, just gas, falling directly into darkness. This direct collapse mechanism solves a puzzle that has haunted astronomers since Webb first began combing the early universe. How did supermassive black holes grow so large so quickly? Traditional black hole formation is slow. Start with a stellar mass black hole, feed it over hundreds of millions or billions of years, and eventually it might reach millions or billions of solar masses. But Webb has found monstrous black holes lurking just 600 million years after the Big Bang, far too early for that gradual growth. Direct collapse black holes offer a shortcut. Instead of starting small, they begin life already enormous, perhaps with masses millions of times greater than the Sun. From there, they only need modest feeding to become the ancient giants Webb observes. In the Infinity Galaxy, We are watching this process unfold while it is still in progress. The black hole between the galactic cores is actively feeding on the gas flowing around it, growing even as we study it. This is not a static relic. It is a live birth. But as wild as direct collapse is, Webb has also uncovered black holes that break the rules in a different way, by eating faster than physics says they should. Hidden among thousands of X-ray sources in the distant universe, astronomers found a supermassive black hole known as LID 568 that appears to be devouring matter at 40 times its theoretical limit. Every black hole has what is called an Eddington limit, a balance point where the outward pressure of radiation from incoming material matches the inward pull of gravity. Feed a black hole too quickly, and the infalling gas heats up and radiates so intensely that it blows away the rest of the material, effectively choking off its own food supply. It's like trying to drink from a fire hose. Beyond a certain flow, the force pushes the water away from your mouth. Yet somehow, LID 568 is managing to drink from 40 fire hoses at once. By combining Webb's infrared vision with X-ray data from NASA's Chandra Observatory, astronomers were able to isolate this extraordinary object from the cosmic background noise. Its energy output and spectral signatures reveal a feeding rate that defies the Eddington limit, suggesting that either our understanding of that limit is incomplete, or special conditions around the black hole allow it to bypass the rules. This has enormous implications for how fast black holes can grow. At such extreme accretion rates, a black hole could gain most of its mass in a single episode. A short-lived but intense feeding frenzy. Instead of slow, steady growth over billions of years, early black holes may have gone through bursts of rapid expansion, each one increasing their mass by an order of magnitude in a relatively brief period. The physics of this process remains murky. Perhaps the geometry of the gas flow channels radiation in certain directions, allowing material to keep falling in despite the intense energy output. Perhaps magnetic fields and turbulence create pockets of low radiation pressure. Whatever the answer, LID 568 shows that black holes in the early universe were not politely nibbling. They were tearing into the cosmic buffet with ferocity. And they were not the only structures behaving in unexpected ways. When Webb turned its gaze to massive galaxies in the early universe, it found some that had simply stopped, scattered across epochs when galaxies should have been at their most productive, turning gas into stars at furious rates. Webb found systems that were already dormant. Astronomers call them sleeping beauty galaxies. They are massive, rich in old stars, but show almost no signs of new star formation. It's as if a bustling city halted all construction at the height of its growth and then just sat there, unchanged, for billions of years. In theory, young massive galaxies should be flooded with cold gas from the cosmic web, feeding ongoing star formation. Instead, these galaxies appear to have shut down early. Some theories blame feedback from their central black holes, jets and winds that heat or blow away the gas needed to form stars. But in many cases, the timing doesn't fit. The galaxies seem to have gone quiet before their black holes became active enough to do such damage. Another possibility is that they burned through their gas with incredible efficiency, forming stars so rapidly that they exhausted their fuel supply in a brief burst of cosmic activity. That would imply star formation rates far beyond what current models consider normal. Or perhaps, once again, we are seeing a process unique to the early universe, a combination of environmental effects, dark matter structures, and feedback cycles that has no modern analog. The message is the same. Galaxy evolution is not a smooth, predictable arc. It is full of abrupt transitions, dead ends, and mysteries. And some of the strangest mysteries are not found in galaxies at all, but in the lonely worlds drifting between them. Webb has examined the atmosphere of a rogue planet known as SIMP 0136 Pozoro933, a world with no star of its own, drifting freely through the galaxy, lit only by the faint warmth of its interior. What Webb saw there does not resemble any weather system on Earth. The planet's atmosphere is layered with metallic clouds, an exotic stack of mineral vapors. Near the bottom, thick clouds of iron form and condense, creating storms where molten metal condenses and falls as iron rain. Higher up, a second layer of clouds made of magnesium-rich silicate minerals, like forsterite, forms a separate weather system. These are not delicate water droplets. They are clouds of rock and metal suspended in a boiling sky. Infrared observations reveal that both cloud layers are patchy and constantly shifting, driven by the planet's rotation and internal heat. The iron clouds and magnesium clouds do not always move in sync, creating a three-dimensional patchwork of changing brightness and temperature. Above these mineral clouds, Webb detected strange hot spots, regions of intense heat apparently powered by radio auroras. These are cousins of Earth's northern lights, but on a far more violent scale, driven by a magnetic field vastly stronger than anything in our solar system. Charged particles from interstellar space spiral along the planet's magnetic field lines, slamming into the upper atmosphere and dumping energy into small regions, heating them to extremes. The result is an atmosphere that blends mineral rain, metallic storms, and electromagnetic fire. All of it on a world with no sun. If one rogue planet can host such wild weather, there may be countless others in the galaxy, each with its own bizarre atmospheric chemistry, clouds of titanium, storms of glass, fogs of carbon dust. But the violence is not limited to planets. Webb's deep field images have also captured galaxies being literally torn apart by their environments. One such system, nicknamed the Cosmic Owl, for its two bright central regions and surrounding arcs of gas and dust, belongs to a class known as jellyfish galaxies. These galaxies move through dense regions of hot gas, often in galaxy clusters, at such high speeds that they experience a kind of cosmic headwind. This headwind exerts pressure on the galaxy's gas, blowing it backward and stripping it away in long trailing tendrils. Those tendrils are the tentacles that give jellyfish galaxies their name. Vast streams of stars and gas stretching hundreds of thousands of light years into space. The cosmic owl is shedding material as it flies, leaving behind trails of gas that are compressed and shocked by the surrounding medium. In those tentacles, new stars are born, lighting up the stripped material in bright knots of blue. The galaxy is being eroded and reshaped by its environment. But in the process, it is also seeding intergalactic space with new stellar populations. Its children are being pulled away from home, destined to live out their lives far from the galaxy that birthed them. And finally, as if all this weren't enough, Webb has looked at the chemistry of some of the earliest galaxies it can see and found something that breaks one of our last comforting assumptions: that complexity takes time. In the earliest epochs after the Big Bang, the universe's chemical palette was simple: hydrogen, helium, almost nothing else. Every heavier element, carbon, oxygen, nitrogen, silicon, iron, had to be forged in the hearts of stars and spread via supernova explosions. This is a slow, cumulative process. First-generation stars live and die, enriching their surroundings. Second-generation stars form from that enriched gas, adding more metals and so on, across billions of years. And yet Webb has found young galaxies, less than 1 billion years after the Big Bang, already rich in heavy elements. Their spectra show surprisingly high levels of oxygen, carbon, and nitrogen. Chemistry that should require multiple cycles of star birth and death. One possibility is that the first stars were nothing like the stars we know today. These so-called population 3 stars may have been monsters, hundreds of times more massive than the Sun, burning hot and fast for only a few million years before exploding in titanic hypernovas. Each such explosion would have flooded its surroundings with newly minted heavy elements, enriching vast regions in a single event. If the early universe was full of these stellar behemoths, then the chemical clock we've been using to estimate evolutionary timescales is wrong. Complexity, at least in terms of elemental composition, may have emerged far more quickly than we assumed. Another possibility is even more radical: that some unknown process, perhaps related to exotic particle physics or early universe phase transitions, contributed to heavy element formation in ways we have not yet discovered. Whatever the truth, the message from Webb is clear. The early universe was not a simple, slowly awakening cosmos. It was a place of extremes: rotating structures, impossible black holes, hyperactive galaxies, rogue worlds with metallic storms, comets older than our sun, and chemical complexity appearing almost as soon as the first light broke through the darkness. We thought we were mapping a familiar sky with sharper tools. Instead, we have opened a door onto a universe that feels, in many ways, brand new. In the earliest ages of the cosmos, when the first stars were just beginning to ignite, something extraordinary happened with the chemistry of reality itself. James Webb's observations suggest that heavy elements, oxygen, carbon, nitrogen, the very atoms that would one day build planets, oceans, and living cells, were spreading across space far faster than our theories ever allowed. One way to explain this is to imagine stars so massive, so bright, and so short-lived that they barely resemble anything in the modern universe. These hypothetical giants, called population 3 stars, could have been hundreds of times more massive than our Sun, burning through their nuclear fuel in just a few million years before exploding in titanic hypernovas. Those explosions would have acted like cosmic forges, flooding vast regions of space with freshly minted heavy elements in a single generation of stars. Such monsters don't exist today. But in the extreme, dense conditions of the young universe, they might not only have been possible, they might have been common. The second possibility is even more unsettling. If some unknown process was creating heavy elements directly in the early universe, bypassing or enhancing traditional stellar nucleosynthesis, then our entire understanding of cosmic chemical evolution is incomplete. There might have been exotic pathways operating in the universe's youth, driven by violent phase transitions, high energy fields, or physics we haven't yet discovered, that seeded space with complexity far earlier than we thought. And that changes everything. If metals appeared sooner, then rocky planets could have formed sooner. Atmospheres rich in interesting chemistry could have appeared sooner. The building blocks of life as we know it, carbon chains, water-bearing minerals, complex molecules, might have existed when the universe was still in its infancy. We might not be the first possible chapter in the story of life. We might be very late. While Webb was rewriting the history of cosmic chemistry, it also turned its gaze much closer to home, to our nearest stellar neighbor, and uncovered one of the strangest disappearing acts in modern astronomy. In the Alpha Centauri system, just over 4 light-years from Earth, Webb detected a thermal signature consistent with a giant planet orbiting Alpha Centauri A, a sun-like star that has long been a focus of our dreams of interstellar travel. The signal suggested a world roughly the size of Neptune, orbiting in a region that might be marginally compatible with liquid water depending on its atmosphere. For a brief moment, it looked like the closest potentially habitable exoplanet ever found. And then it vanished. Follow-up observations with Webb failed to detect the planet at all. The thermal glow that once stood out clearly against the background was simply gone. No gradual fading, no clear periodic cycle. Just an absence where a possible world had once appeared. Astronomers scrambled for explanations. Perhaps the planet follows an extremely elongated orbit, spending most of its time far from the star, cold and invisible, only briefly swinging inward where its heated day side can be seen in infrared. But in a binary system like Alpha Centauri, such an extreme orbit should be dynamically unstable, quickly disrupted or ejected by the gravitational pull of Alpha Centauri b. Another idea is that the planet is shrouded in a thick, variable dust cloud or ring of debris that sometimes radiates strongly in infrared and sometimes blocks its own emission, making the world appear and disappear in Webb's vision. That would mean the Alpha Centauri system is far more active and chaotic than we thought, with ongoing collisions or disruptions constantly stirring up debris. A more radical possibility is that we're catching a planet in the act of formation, embedded in a residual disk of gas and dust long after such material was expected to be gone. If that's true, then planet formation might be a much longer, more episodic process than our models suggest, still active in a star system billions of years old. The most unsettling interpretation, however, is that what Webb saw wasn't a planet at all. Maybe the thermal signature came from a warm clump of debris, a failed starlet, or some transient phenomenon that doesn't fit neatly into our categories. Whatever the truth, the Alpha Centauri Vanishing Act is a reminder that even in our immediate cosmic neighborhood, we are still stumbling in the dark. If a world can appear and disappear right next door, how many more strange planets are out there, hiding in plain sight just beyond the edge of our understanding? While astronomers wrestled with vanishing worlds, Webb was uncovering something even more profound, stitched across the largest structures in the cosmos. Invisible networks of magnetism older than any galaxy and as structurally complex as the neural pathways in the human brain. Spread across the cosmic web, the vast system of filaments and nodes that connects galaxies and clusters. Webb detected signs of ancient magnetic fields threading through intergalactic space. These are not simple, uniform fields. They form intricate patterns, with nodes, bridges, and branching hierarchies that eerily resemble the connectivity maps neuroscientists use to study brain networks. The similarity is so striking that researchers have begun applying mathematical tools from neuroscience to cosmic magnetism. Standard cosmological models assume that magnetic fields in space arise gradually as galaxies and stars form, with rotating plasmas, stellar winds, and supernova explosions amplifying weak seed fields over billions of years. But the primordial magnetism Webb is seeing appears to predate many of these structures. The fields seem to have been there from the universe's youth, influencing how gas collapsed into the first stars and galaxies, shaping the flow of matter before any visible structures fully emerged. Magnetic pressure might have slowed or redirected collapsing clouds. Magnetic reconnection events, where field lines snap and reconnect, could have heated gas, triggered bursts of star formation, or suppressed it in some regions. Even more disturbing, these fields are not static. They show signs of evolution, with connections forming and dissolving across cosmic time. Vast magnetic storms appear to rage across galaxy clusters, affecting star formation and gas dynamics on scales that dwarf any individual galaxy. It's as if the universe's scaffolding is not just gravitational, but also electromagnetic, wired with a hidden circuitry we're only now beginning to trace. If primordial magnetism is this complex and this influential, it could help explain many discrepancies in our models of structure formation. Why some regions formed galaxies more quickly than others. Why matter clumps in certain ways. Why some cosmic voids are emptier than expected. It also hints at something deeper, that the universe has an intrinsic tendency toward complexity and network-like organization, long before life ever arose to mirror those patterns. While invisible magnetic networks shape the cosmic web, a much closer and more familiar monster is sending out signals that reality itself might be fraying at the edges. At the center of the Milky Way, 4 million times more massive than the Sun, lurks Sagittarius A, the supermassive black hole that anchors our galaxy. We've long considered it relatively quiet, a sleeping giant occasionally flickering as it nibbled on stray clouds of gas. Webb's continuous near-infrared monitoring has shown a different picture. Sagittarius A is not calm at all. It is restless. Over dozens of hours of observation across a year, Webb observed the region around the event horizon, bubbling and seething with chaotic brightness fluctuations, like boiling liquid seen from a great distance. Then, seemingly at random, enormous flares erupted, boosting the black hole's brightness by factors of 10 or more before fading away. No clear rhythm, no repeating cycle, no steady heartbeat, just a kind of unpredictable, chaotic pulsing. Some of this can be explained by turbulence in the accretion flow. Magnetic fields twist and snap in the superheated plasma spiraling in, compressing gas and briefly increasing its brightness. These are like cosmic lightning strikes flickering through the disk, but the larger flares may be something else. Huge clumps of matter crossing the photon sphere, that strange region where light itself orbits the black hole in unstable loops before either falling in or escaping. When those clumps disrupt the delicate balance of orbits near the event horizon, they may trigger brief, intense outbursts. The key point is where all of this is happening, in a region where gravity has nearly reached its maximum strength, where space and time themselves are warped almost to the breaking point. The chaotic, patternless nature of Sagittarius A's brightness changes hints that purely classical physics may not be enough here. Quantum effects could be creeping up to macroscopic scales, influencing how matter and radiation behave in ways we don't yet understand. The behavior of our own central black hole feeds into one of the deepest mysteries in physics. What happens to information that falls into a black hole? If the radiation from near the event horizon is truly random, it might imply that information is being scrambled or destroyed in ways that challenge quantum mechanics. On the other hand, subtle patterns we haven't yet recognized might hold the key to a new, unified theory of gravity and quantum physics. While Sagittarius A whispers about the breakdown of our theories at the edge of a single black hole, Webb's wide-field surveys reveal that invisible forces are tearing apart entire galaxies and clusters in events driven not by ordinary matter, but by the elusive, mysterious substance we call dark matter. In massive galaxy clusters, gravitational cities containing hundreds of galaxies, Webb has found sprawling, faint streams of stars and gas stretching for millions of light years, like ghostly bridges connecting systems that should have nothing to do with one another. These stellar streams are the shredded remains of galaxies that have been torn apart, not by visible collisions, but by immense concentrations of dark matter. When two galaxy clusters collide, the visible fireworks, shocks in hot gas, arcs of X-ray emission, bursts of star formation, are just the tip of the iceberg. Beneath it all, their dark matter halos slam through each other like invisible titans. The gravitational forces in these encounters are so extreme that they can strip stars from their home galaxies, eject systems into intergalactic space, and reshape the orbits of entire clusters. Webb's infrared sensitivity has finally allowed us to see the faint, low-surface brightness traces of this carnage. The streams it reveals wrap around clusters in delicate, sinuous patterns. evidence of long, slow unspooling of galaxies over billions of years. The violence is everywhere, but it is mostly silent. No light, no radiation from the dark matter itself, only the scars it leaves on the luminous components. These observations suggest that dark matter is far from a passive background component. It is an active sculptor of cosmic structure. Its interactions, whether purely gravitational or something more exotic, are constantly tearing down and rebuilding the universe's architecture. Some simulations imply that dark matter might experience self-interactions, gentle collisions or scattering through unknown forces, that could help explain the clumps and gaps Webb is seeing in dark matter distributions. If true, that would mean dark matter has a shadow physics of its own, a hidden set of rules and forces playing out in parallel to the visible universe. Webb has also peered at one of the most extreme examples of gravity's power to bend reality. A galaxy so massive that its gravitational field warps space-time so severely it creates multiple time-shifted copies of another galaxy behind it. In this astonishing system, light from a single more distant galaxy passes near the foreground behemoth along several different curved paths. Each path has a slightly different length and gravitational delay. So when the light finally reaches us, we see not one image, but several, each representing the background galaxy at a different moment in its history. In one image, the galaxy is slightly younger, bursting with newly formed stars. In another, it's more mature, its star formation slowing. We are quite literally watching its past and less past selves side by side. To produce such extreme lensing, the foreground galaxy must contain an enormous amount of dark matter packed into a dense, lumpy halo. Webb's data show that this halo is not smooth. Instead, it contains substructures, clumps and voids of dark matter that standard models struggle to explain. Space-time is being deformed in intricate, detailed ways that reveal the fine-grained distribution of invisible mass. These systems act as cosmic laboratories for general relativity, pushing Einstein's equations to their limits. In such intense gravitational fields, the distinction between classical space-time and quantum gravity may begin to blur. If we could measure these lensing effects with enough precision, we might catch the first hints of how gravity behaves when reality itself is under maximum strain. As if all of this weren't enough, Webb has turned up evidence that stars themselves are not the serene, solitary furnaces we sometimes imagine, but often end their lives in acts of cosmic cannibalism. Binary and multiple star systems, once thought of as stable partnerships, can transform into feast and victim. In close binaries, the more massive star ages faster, expands, and spills its outer layers toward its companion. Material forms a swirling accretion disk around the receiving star, heating to extreme temperatures, emitting a brilliant glow. At first, this feeding is steady, but as the mass transfer accelerates, the system can tip into catastrophe. White dwarfs, dense remnants of sun-like stars, can gorge on material until they reach a critical mass and trigger thermonuclear explosions that rip them apart in Type Ia supernovae, briefly outshining their entire host galaxies. Neutron stars and stellar mass black holes can do something even more dramatic. As they devour their companions, they can unleash kilonova explosions and gamma-ray bursts, forging heavy elements like gold, uranium, and platinum, and flinging them into space. Webb's infrared eyes can peer through the dust that usually hides such events, tracing the life cycle of cannibal systems from the first trickles of stolen gas to the final, blinding detonation. These feeding frenzies are not rare curiosities. They may be one of the primary ways the universe enriches itself with the heavy elements that build planets and bodies and bones. Every ring of gold, every circuit board, every blood cell carries atoms forged in the fires of stellar violence and cannibalistic explosions. It's a humbling thought. The jewelry on a finger, the metal in a satellite, the iron in our blood, all are relics of acts of cosmic destruction. Piece by piece, Webb's discoveries paint a picture of a universe where the fabric of reality itself seems under constant stress. Gravitational anomalies around some objects don't match our predictions perfectly. Space-time appears smooth and continuous on large scales, and yet hints of deeper cracks are beginning to appear. Some lensing patterns don't fit any known distribution of matter. Certain regions around black holes and galaxy cluster cores emit energy in ways that defy our current understanding. Theoretical physics has long predicted that at the smallest scales, space-time should not be smooth but foamy. A quantum sea of fluctuations and virtual particles known as quantum foam. Normally, these effects are far too small to notice in the everyday universe. But Webb's observations suggest that under extreme conditions, near event horizons, in the densest cluster cores, or around hypothetical defects known as cosmic strings, this foam might be poking through into the macroscopic world. Cosmic strings, if they exist, would be one-dimensional cracks in space-time, relics of phase transitions in the early universe. They would warp space around them in distinctive ways, creating sharp, linear lensing effects and odd distortions in the background. Webb has identified several candidates for such phenomena, structures that don't behave like any normal arrangement of matter and light. If these really are space-time defects, then the universe still bears scars from its birth, cracks that never fully healed. There are also hints of vacuum decay-like events, regions where the underlying quantum vacuum seems to jump to a slightly lower energy state, releasing bursts of energy in the process. Such events, if confirmed, would be direct evidence that even empty space is not truly stable, but sits on the edge of deeper transitions we barely understand. The more we look, the more reality appears less like a rigid, eternal stage, and more like a dynamic, fragile medium, one that can tear, buckle, and reorganize itself under enough stress. All of this leads to one of the most radical ideas gaining traction as Webb's data accumulate: that our universe itself might be the interior of a black hole inside a larger cosmos. In this black hole cosmology picture, what we call the Big Bang was not the creation of everything from nothing, but the moment our region of space crossed the event horizon of a gigantic black hole in a higher dimensional reality. From the outside, matter fell inward. From our perspective, space expanded outward. The accelerating expansion we attribute to dark energy might be a side effect of our continued infall toward the central singularity, with time dilation and space-time curvature combining to create the illusion of faster and faster expansion. The coordinated galaxy spins that Webb sees on cosmic scales would then simply be the imprint of the parent black hole's rotation, carried into the new universe it spawned. The primordial black holes that appear older than the first stars might be fragments of the larger structure that existed before our cosmic horizon formed. If this is true, then black holes in our universe may also be giving birth to new universes inside them, each with its own space, time, and physical laws. Our cosmos would be just one bubble in an endless hierarchy of black hole universes, each contained within another. It is a staggering, vertigo-inducing vision. Reality as a nested infinity of worlds within worlds, with universes being born not in empty hyperspace, but in the hearts of collapsing stars and galaxies. James Webb was launched to sharpen our picture of the universe, to give us clearer views of familiar objects and fill in a few missing details. Instead, it has detonated our confidence. The cosmos, it reveals, is not a clean, orderly clockwork, but a wild, violent, creative chaos where galaxies form too fast, black holes grow too big, planets appear and vanish, magnetic fields behave like neural networks, dark matter tears galaxies apart, and even space-time itself may crack and froth under stress. Every time we point Webb at a new region of sky, it returns not just beauty, but questions. Deep, unsettling questions that cut into the foundations of physics, cosmology, and our own sense of place. We are not living in a gentle universe that quietly welcomes life. We are balanced on the edge of a churning, unstable reality that only occasionally assembles the right conditions for complexity to arise. And yet, against impossible odds, here we are, a species on a small, rocky world around an ordinary star, building telescopes that can look back to the dawn of time and catch the universe in the act of breaking its own rules. Perhaps that is the real revelation of James Webb. Not just that the universe is stranger, darker, and more dangerous than we ever imagined, but that our curiosity is strong enough to face it. We are fragile, temporary beings staring into an ocean of fire, ice, and warped space-time. And even as reality bends and cracks on unimaginable scales, we keep watching, keep questioning, keep trying to understand. In a universe that seems perfectly willing to tear itself apart, the act of looking up and trying to make sense of it all might be the closest thing to meaning we will ever find.